Now we ended the last section with really tricky factoring. Factoring a trinomial when a is not 1 is very, very difficult, and especially if you're going to do trial and error, that's really difficult. So then we learned this kind of easier method with factoring by grouping, but it's still got a lot of steps, right? So we're going to move from there to the simplest factoring. We're going to factor binomials, very special binomials. Now, the last section was really trinomials for ax squared, these ones. These are trinomials because it's got 3 terms. And then we also did this factoring by grouping, which had 4 terms, quadrinomials, something like that. Okay, so we're going to do binomials. If you look here, every single one of these only has 2 terms. So there's some easier methods for doing those. And that's what we're going to run into on these couple pages. So let's start with a squared minus b squared. So a squared minus b squared. Let me give you an example. Hold on. Okay, there it is. I'm going to put it over here on the edge. So I'm going to give you an example, x squared minus 81. So when you look at x squared minus 81, you say, okay, I want double parentheses. I know it's going to be x and x. Now to make the minus 81, it's got to be a plus and then a minus. And then the question is what? What could I put in for numbers so that when I multiply, when I do my first, outers, inners, last, there won't be any middle term. It'll disappear. And the answer is you can do what we learned about in section 6.1, which is, or 6.2, which is binomial conjugates. You can multiply it so that they're the same, but with one positive and one negative. Let me scroll back and find you binomial conjugates because you learned them. You might have forgotten them. There they were. Haha. So when you have a plus b times a minus b, it ends up being a squared minus b squared. See, here's this example right here. So what we're doing is we're saying, okay, instead of going this way, 4x plus 7, 4x minus 7, to 16x squared minus 49, we're actually going to go backwards. Take 16x squared minus 49 and go back to the binomial conjugates. When you do that, it'll work out when you try to multiply. If you try to FOIL, multiply this out, the first is going to be x squared. Hold on, I got to get the problem. Where is it? There it is. Okay. The first would be x squared because x times x makes x squared. The outers would be minus 9x. The inners would be plus 9x. Minus 9x plus 9x makes it all disappear. That's why there's no x term. And then plus 9 times minus 9 is minus 81. All right. So there's a little example. Matter of fact, I'll put a little example right next to it. So we have that. Okay. So now what does that mean for our general form? Well, it means that instead of writing a squared minus b squared, we're going to be able to say a minus b times a plus b. And of course, the order doesn't matter with the plus and the minus. That's fine either way. All right, so let's practice it. And I know it seems crazy, but this is the easiest factoring you possibly can imagine. This is as easy as it gets. If you don't see a middle term on these things, that's a sign. Notice, by the way, this only works for difference of squares. The box right there says difference, meaning subtraction of 2 perfect squares. Right? So these things have to be perfect squares, like 4, 9, 16, 25, and so on. Okay. Actually, it'd be a good idea to list those. So let me bring them up. So perfect squares would be 1, because that's 1 times 1. 2 times 2 makes 4. 3 times 3 makes 9. 16. Let's see, 25, 6 times 6 is 36, 49, 64, 81, 100, 121, 144. So those are some of the perfect squares. They're all the numbers that would form the diagonal of a times table if you had a times table. Okay. Oh, of course, I've got to make the font just a tiny bit smaller. My life wouldn't be complete without some kind of mess up. Okay. All right, so if that's the case, look at this. This is the difference of squares because 4 is a perfect square and 25 is a perfect square. So what you do is you break it up into 2 parentheses. And you got to break it up perfectly. So what you do is you take the square root of 4. So you say, okay, square root of 4 is 2. So if I do 2x and 2x, that'll be perfect because then I'll have half of it on one side and half of it on the other. Then I do minus 5 plus 5. Or if you like plus 5 minus 5, it's fine. They're exactly the same, but one's a minus and one's a plus. They are binomial conjugates. Binomial because they're 2 terms. Conjugates because they're exactly the same except for the middle sign is negative on one, positive on the other. Now if you FOIL this, you'll get the same answer we got. So you'll say 2x times 2x is 4x squared plus 10x minus 10x. For the outers is plus 10x, inners is minus 10x. They're gone. No middle term. That's why we have no x term over here. And then minus 5 times positive 5 makes minus 25. It's as simple as that. Now, what we can do to make it harder is make it seem like they're not perfect squares to begin with. But au contraire, this one is. You just don't realize it. What you want to never forget is GCF. GCF kind of becomes the redheaded stepchild of factoring. We sort of expect it to just be there. Maybe the Cinderella would be a better way to say it. We expect it to be doing work for us all the time, but we don't often mention it. There is a perfect square, a greatest common factor that you can take out of this to make this a perfect square. If you take a 2 out and an a out, because they both have an a, oops, there's a b squared back here, then this will work. You'll have an a squared in the front because there were 3 a's there. You took 1 out. That left you 2 left over. And then 18 divided by 2 is 9. So that, and then a b squared. Now, both of these are perfect squares. 9 is a perfect squared, and of course squared is a perfect square, and squared is a perfect square. So this is equal to 2a times, I'm going to double parentheses, a is going to go in the front of each of them. One gets a plus, one gets a minus, and then all you have to do is figure out how can you break up 9 evenly. Well, it's got to be the square root of 9, which is 3. Now, 3 times 3 will make you 9, everything will be great, but you won't need these b's in there as well. So you need to make it so it's 3b and 3b. This will work. If you don't believe me, try to FOIL it. You always can double check all your answers for the factoring formula sections, because you can multiply all this stuff. A times a is a squared. Negative 3ab, positive 3ab means there is no middle term. 3 times a negative 3 is negative 9. B times b is b squared. And then the 2a is just sitting there in front. So you just leave it right there. Done. All right, let's do it some more. Okay, so C is kind of a similar boat to the last one. It looks like it won't be alike, but it is. So, it looks like it won't be difference of squares, but it is. Okay, so let me give it to you. Now remember, we never like our leading coefficient being negative. That's just bad. And this author just loves to give those to you because they mess with your mind. So what you're going to do is you're going to factor out a negative 5 and an x, because both terms have an x to give. Now if you take the negative 5 and an x out of here, what you're left with is x squared minus 9, because the sign is going to change. If you take out a negative and it was a positive number, positive 45 divided by negative 5 would make negative 9. Or put it this way, you need to be able to multiply and get back what you had. Negative 5 times negative 9 makes positive 45. There's no x anymore because you took the one x it had to give and you put it right there. Okay, now we're not done. We got to finish it out. So you're going to write negative 5x, just leave it in front, x minus 3, x plus 3. Because the square root of 9 is 3. Diggity done. All right, now before I tackle D, I actually need to kind of make a little note. So let me give you some examples right here. So let's talk about the sum of squares. Sum of squares note. I'm going to give you a couple examples real quick. So let's do x squared plus 81. Okay? I know we did x squared minus 81 up above. Okay? Right here, x squared minus 81. So let's talk about summing of 81. Now what students always want to try to do is x plus 9, x plus 9. Now what's going to happen with this? If you tried to FOIL this out, let's see what would happen. It'll be x squared plus 9x plus 9x plus 81. You're going to get the x squared and the 81, but you're also going to have this whole thing in the middle that you shouldn't have. See the problem? This doesn't work. It ain't going to happen, right? So then you could try minus and plus, but minus and plus would have left to negative in here, subtraction. So this is prime. This is what I'm going to get at down here. I lied to you a little bit. It's not always prime. I'm bad. It's prime. So scratch off the word prime always. Hold on. Let me put that in. There we go. It's not always prime. It's prime as long as there's no GCF. As long as there's no GCF. Okay? Let me add all that in. Now, what do I mean by that? Let me give you another example. Okay, bear with me here. What if it was, what was the one we just did? What if it was 4x squared plus 25? I don't want to do that. How about 4x squared plus 36? Okay, well, that has a GCF. It's 4, right? So you can take 4 out. That will leave you x squared plus 9. Now this part here is a sum of squares, so that part of it is prime, but the actual problem itself isn't prime because you took out a GCF. Okay, so it's not prime because we factored out a GCF. The x part, x squared plus 9 part is prime. Part is prime. Okay, everybody get what I'm getting at right down here? So that's what I'm saying here. The sum of squares is always prime, like x squared plus 9 is prime, and it is, as long as there's no GCF. If there's a GCF that you take out, that means that the actual answer is not prime, because we took a 4 out. That makes it not prime. This little part of it is prime, but overall it was not prime because you took out a greatest common factor. All right, so, and there's kind of my examples, so they're kind of in the backwards thing, but that's okay. All right, so this was, instead of example, this was actually my example, all for that sum of squares business, okay? All right, so now I want to take that idea and go back to 81k to the fourth minus 16. So let's look at that for a second. Okay, 81k to the fourth. Now, it is a difference of squares. I swear, these are both perfect squares. So 81k to the fourth minus 16. All right, we can break this up perfectly because 81 is a perfect square and 16 is a perfect square. This is 9k squared minus 4 times 9k squared plus 4. You with me? You dig? Right? It's because the k squared times k squared makes k to the fourth, right? Everybody looking at it, making sense? Okay, so you'd think, oh, I'm done. Oh, but you're not, right? So not by a long shot. So if you're not done, right, there must be something else you can factor. And I want you to look at this one right here. You can factor that. In other words, it breaks down further. So let's see here. How does it break down? Well, it's a difference of squares. 9's a perfect square, 4 is a perfect square, and that's, my friends, is subtraction right there. So this is 9k, not 9k, I'm losing it, 3k minus 2 times 3k plus 2. And then this part just sits there because that part is prime. It's what we just talked about down below, right? Sum of squares is prime, right? As long as there's no GCF, and there isn't. 9 and 4 don't have anything in common. Now we are done. Right? We broke up the difference one that like we could, and we left the sum one alone because the sum one didn't have a common factor, and therefore we're done with it. Okay. All right, so we're done with sums and differences of squares. Next time we're going to work on cubes, and that formula should really be at the top of the next page, but that's what we're going to work on for the next problems. All right, so I'll see you back here for that.